Here we go with topic 7. We are on our final part of it, which is molecular polarity. So we're still focusing on our molecular structures, our covalent compounds, and we are going to use the 3D shape of our chemical to help determine if a molecule is polar or nonpolar. So before we jump completely into the whole molecule, let's review polar bonds. So electronegativity is what controls polarity. So it is a measure of the attraction of bonded electrons. All right, we reviewed this towards the beginning of this unit. So electronegativity is that attraction of bonded electrons. It's a measure of how attracted they are. So you can imagine our atoms, two atoms bonded to each other. I'm going to use hydrogen and fluorine as an example. And those shared electrons are kind of in this tug-of-war with each other. The two atoms are trying to attract the electrons. The one that has the greater electronegativity is the one that attracts the shared electrons more. So more electronegativity in an atom, or an atom is, the more it attracts the electrons shared in that bond. Bonded elements with the same electronegativity, something like HH, FF, so any of our diatomic elements, will be nonpolar as they equally share their electrons. They have the equal electronegativity. The exception to this is CH. We also consider that one nonpolar in AP Chem. Elements with different electronegativities will have polar bonds, like carbon and fluorine. Fluorine is more electronegative, so it attracts the electrons more, and the bond is polar. So we've got two examples down here. We've got H and F, and then we've got nitrogen and nitrogen. So hydrofluoric acid, that's what HF is. We'll deal more with acids later. And then we got our nitrogen molecule. The coloring on these pictures and this kind of bubble around them represents the electron cloud. And the coloring represents the electron density. So that's basically where the electrons hanging out more. Well, on our HF molecule, we can see the red side where we have high electron density is towards fluorine. So that means fluorine has more electrons attracted to it. It's more electronegative, and hydrogen has that low electron density. So that means it's a more positive end of our molecule. So we have a partial negative side and a partial positive side, right? So we get that polar bond, that dipole occurring. Then two nitrogens, we have that nice kind of gray, which falls right in the middle there. And that means that it's nonpolar. Both have equal electronegativity, so they're both attracting the electrons equally. So now we are going to expand this from individual bonds to looking at entire molecules and looking at their polarity. To determine if a molecule is polar, we have to take into account multiple things. The polarity of the bonds, which we've analyzed so far, being able to draw those dipoles on the bonds, the 3D shape, which we've now looked at, and if there's symmetry in the molecule. Are the dipoles symmetrical, or are they and reinforcing each other, or are they canceling each other out? So what does it mean to be a polar molecule? Well, the electrons would have to be unevenly distributed around the central atom, causing a concentration of negative charge and positive charge. This unequal distribution of charge makes the molecule polar. If the charge is equally distributed or symmetrical, then it is a nonpolar molecule. So let's start by looking at a polar molecule example. Water is probably our most known polar molecule, and one of our most important ones as well. So what makes it polar? Well, let's just start with our drawing of water here on the left. We've got our Lewis dot structure, and we can see that we've got our two hydrogens bonded and our two lone pairs. Now, this is a great representation of the bonding that occurs and that it has lone pairs, but it's not the best representation of the shape of our molecule. So it is a good idea to start drawing water bent. So we know that water has polar bonds because oxygen is more electronegative than hydrogen. So we can draw the dipoles on this. If we looked at that first Lewis dot structure, it would be a little bit misleading because it would look like the two dipoles are pointing at each other. But in reality, it has a bent structure, a bent 3D shape. So the two dipoles reinforce one another, causing the electrons to be more concentrated towards that oxygen on one part of the molecule. So we get those two dipoles. We could actually draw a single dipole for the whole molecule. I'll do that on the side here, showing that the electrons are being attracted to the oxygen and being pulled away from the hydrogen, making that side more positive. If we look at the electron cloud model on the right side, we can see that the area of high electron density is around the oxygen and low electron density is around the hydrogen. So that means our hydrogen side is partially positive while our oxygen side is partially negative. Because we have this difference in that charge density, we have a polar molecule. It has that dipole that we can draw for it. Now, if the dipoles cancel each other, if they go in the opposite direction of each other, then we'll have a nonpolar molecule. So we're going to see an example of that next. So another example that's great for us is carbon dioxide. So this is a good example of a nonpolar molecule. So what makes it nonpolar? It does have polar bonds. So we've got a bond between a carbon and an oxygen. Oxygen is more electronegative, so it will attract the electrons more than carbon. But I could draw an equal and opposite dipole towards the other oxygen. So even though it has polar bonds, it also has a linear shape. And because of the linear shape, the dipoles cancel one another out, causing the electrons to be concentrated on each end of the molecule. Since we have this symmetry, the molecule is nonpolar. All right, so we do get a little bit more of a positive charge in the middle and a slightly negative charge on each end, but it's all the two ends are equal to each other. So we do not get a polar bond molecule. We cannot draw a single dipole towards one direction for the whole molecule. We can't say that the electrons all go towards that oxygen or all go the opposite way towards the other oxygen. That doesn't work. So this is a nonpolar molecule. Carbon dioxide is one of our most common nonpolar molecules, and it's due to the linear shape. If it was a different shape, like our water was bent, it would be polar. So you can have polar bonds like this and be a nonpolar molecule, looking at the whole structure. Or like in water, we can have polar bonds and have a polar molecule. So the polarity of the bonds doesn't necessarily predict the polarity of the molecule. We have to take into account the three-dimensional shape, which is why drawing dot structures and being able to determine the shape is so important. All right, we're going to talk through a few molecules here and see how we can analyze these to determine if they are polar or nonpolar molecules. So our first one here, we've got our carbon-hydrogen bonds. So these would be nonpolar. We wouldn't be able to draw a dipole for them, but we have a carbon-oxygen bond here. So that would have some polarity to that bond. Along with this, we should recognize that it has three bonding domains, and that makes it trigonal planar in shape. So with something that's trigonal planar, we've got our central atom and then three atoms bonded to it on equal and opposite sides. Well, in this case, we've got just one of those bonds being polar. So the electrons are shifting towards that oxygen. So we are definitely going to have a negative side to this molecule and a positive side to this molecule. That tells us that it is polar. Right? The electrons are concentrated on one side of the molecule. There's no second dipole to cancel this one out. All right, our next one is CH4. So we cannot draw dipoles on any of these bonds, and it has 4 bonding domains. That makes it tetrahedral in shape. And if they're all equal and nonpolar and tetrahedral, then this would make it nonpolar. Now let's do a second example with this one, just as a side note. Say I changed one of my hydrogens into a fluorine atom. Now fluorine is very electronegative, so we would get a polar bond created between that carbon and that fluorine. Because that fluorine is only one of the 4 atoms on that molecule, it's going to make that part of the molecule more negative, where fluorine is, that partial negative, which means the other side towards carbon and the hydrogens would be partially positive. That would make it a polar molecule. So replacing one of those hydrogens with something like fluorine or chlorine, something like that, that's more electronegative, is going to make this be a polar molecule. Now let's take that one step further really quick. If I replaced all of these hydrogens with fluorine and made them all super electronegative atoms, we would get 4 dipoles, all pointing to those fluorines. Now remember, this is a tetrahedral shape. All of the bonds, they're not at 90-degree angles, right? They're in these 109.5-degree angles. It's this little tripod with a bond sticking up towards the top, but they're still pulling in equal and opposite directions. It's like a 4-way, 3-dimensional tug-of-war, and all of the fluorines are winning, but they're winning equally. So because they're all the same, and they're all pulling the same, that would still be nonpolar. Okay, so when you have a tetrahedral shape and all your atoms match, you're going to be nonpolar. But if they don't match, then we're going to get some electronegativity, higher electronegativity on one part of our molecule, and it's going to cause it to be polar. All right, so matching is nonpolar, not matching is polar. All right, let's look at our last one here. We've got our nitrogen hydrogens. Nitrogen is more electronegative, so we'd have 3 dipoles pointing towards nitrogen. And this one, we've got those 3 bonding and 1 non-bonding pair, so that is a pyramidal shape. So it's like this tetrahedral one up here, but we've replaced a bond with a lone pair. Right, we replace that bond with a lone pair. Let me draw it a little bit better. There's our lone pair sticking up. So we've got this little tripod at the bottom of hydrogens and that really electronegative nitrogen in the middle. So all of our electrons are being shifted towards that nitrogen. So they're all reinforcing one another and all pointing towards the same direction, towards that nitrogen. So we get the positive hydrogens, we get the negative nitrogen, so this is going to be polar. So we can actually summarize our polarity in this table here, thinking about our different structures, our different shapes, and what kind of polarity they might end up with. So if you've got a tetrahedral structure, you've got those 4 atoms attached to our central atom. It will be nonpolar if all 4 atoms match, like CF4, CH4, CCl4, CI4. They're all matching around our central atom. Or if we had like silicon in the middle, that's another thing that can bond 4 times. Otherwise, if they don't match, then it's going to be polar. So for instance, CH2F2. Even if I draw it like this, where it looks like, oh, my carbons and hydrogens are fine, I have my 2 polar bonds with fluorine, but they cancel. They do not cancel, okay? Remember, it is not drawn flat. We're looking at a 3D structure. So any 2 of those could be fluorine. Say this one and this one could be fluorine. So now I've got a concentration of negative charge on this side. Or it could be any 2 of those. And they're equal distance apart. So it doesn't matter which 2 they are, you'd always end up with polarity. So if they match, it's nonpolar. If they don't match, then it's polar. The pyramidal and bent shape also come from those 4 electron domains. They're always polar. The dipoles cannot cancel out with each other. They're either going to be reinforced towards our central atom or reinforced towards the other atoms, but they're always going to be polar. So pyramidal and bent are always polar. Number 3, we've got a trigonal planar shape. So this is similar to tetrahedral. It's nonpolar if all 3 of our atoms match. So if we get that boron with the 3 hydrogens, they're going to pull we're going to have 3 dipoles towards boron, but they all cancel each other because it's like boron is winning that tug of war, but equally on each side. So that would be nonpolar. But if they don't match, like the CH2O that we did earlier, that was one of our first examples there. If they don't match, then it's going to be polar. All right. The bent shape, the one that has 3 electron domains, so where it's the 2 bonds on our central atom and then that lone pair, that one always going to be polar. So either the dipoles are pointing towards your central atom or they're pointing away from your central atom and they're reinforcing each other. They're not opposite of each other. They cannot cancel out. So always polar. And then our linear structure. Our linear structure is nonpolar if our 2 atoms match, like we saw in carbon dioxide earlier. Otherwise, if they don't match, it's polar. So a good example is HCN. Oops. So if I wanted to draw this, we end up with this structure with a triple bond, lone pair. So hydrogen and carbon would be nonpolar bond, but carbon-nitrogen, we get a dipole there. It's pointing towards one side of the molecule. There's nothing to cancel it out, so it would be polar. So our tetrahedral, our trigonal planar, our linear, each of those, they're going to be nonpolar if everything matches around it. Otherwise, they're going to be polar, okay, if they don't match. Pyramidal and bent, always polar. So we do have some patterns to this to help us out. All right, we're going to take a look at some examples and try to determine if these are polar or non-polar molecules. So the first thing we want to do is draw these molecules. Now, some of these we have drawn before, but I will do a quick dot structure for them, and then we'll check their polarity. So BH3, we'd have 3 electrons from boron and 3 from each of our hydrogens total. So we have 6 electrons. Boron, remember, is one of our exceptions to the octet rule. Ooh, that's kind of hard to see. So I'm going to go ahead and bond my 3 hydrogens to boron, single bond them, and that actually uses all 6 of our electrons. And because boron is an exception to our octet rule, it does not need that full octet. This is our whole structure. So we have 3 bonding domains and 0 non-bonding domains. So this would make it a trigonal planar structure. And with trigonal planar, all 3 of these, if I could draw this a little bit better, let me just erase a little bit and move these around. So if I could draw it a little better, our 3 hydrogens would be evenly spaced out around our boron. And if we look at these, they have a slight difference in their electronegativity. Boron would be a little more electronegative. And our
dipoles would all point towards boron. But since everything matches and it's all just reinforcing each other, or excuse me, since they're all canceling each other by pointing all in opposite directions, this would be non-polar. So our trigonal planar, when we have matching atoms all the way around that central atom, it's non-polar. All right, I'll alternate colors here so we can kind of tell the difference. PCl3, so phosphorus gets 5 electrons. We've got 3 chlorines, each with 7 electrons. So that's 21 and 5 is 26. So my phosphorus can go in the middle. I can attach my 3 chlorines with a single bond. And that uses 6 of my electrons. So I now have 20. And we can start adding lone pairs to those outside atoms. 2, 4, 6, 8, 10, 12, 14, 16, 18. So we have 2 left, and any leftover electrons are lone pairs on our central atom. So we have 3 bonding and 1 non-bonding domain. That gives us 4 total. So that's coming from that tetrahedral shape, but we're replacing a bond with a lone pair, so that makes it pyramidal. All right, so we can imagine having that central atom with the 3 little bonds, making that little pyramid shape, and that lone pair on top. So pyramidal is going to be polar. Our chlorines are going to be more electronegative than our phosphorus, so all of our dipoles would point towards the chlorines. So if we had this little pyramid, all of our dipoles will be pointing down towards those chlorines, so this is definitely polar. So we do have to go through this process in order to analyze these. So it is a little more involved, which is why this is the last topic in this unit, right? We had to build towards this. Okay, SCl6. So we've drawn this one before. We end up with, you can always pause and try drawing it. That's good practice. But we end up with sulfur with 6 chlorines around it. There we go. Our total number of electrons, I forgot that. We'd have 6 from sulfur. I'll do that over here. 6 from sulfur plus 6 chlorines, each with 7 electrons. So that gives us 7 times 6 is 42, plus 6 is 48 electrons. So each of these chlorines would get 2 lone pairs, or excuse me, 2 lone pairs. It would get 3 lone pairs to get its total of 6 electrons. Just do those quickly. So around each chlorine is 8 electrons. 8 times 6 is 48. So we've used all 48. Now each of those chlorines would be would create a polar bond with our sulfur. Right? We have all these dipoles going towards our chlorines all the way around. So with that, we would end up with it being non-polar because everything is shared equal in opposite directions. No one wins the tug of war. All right, let's try H2S. So we got 2 hydrogens, that's 2 electrons. Sulfur gives us 6 electrons. So we've only got an octet. We've got 8. So we got our sulfur. Stick our 2 hydrogens on there. We end up with 2 extra lone pairs, so we do that. Now we've got 2 bonding and 2 non-bonding domains, so that gives us a bent shape. Bent is always going to be polar, so if I drew this a little closer to what it would actually look like, we'd have that sulfur atom and the 2 hydrogen atoms, and then our lone pairs sticking up. So our sulfur is going to be more electronegative, so those dipoles reinforce each other, and we get. All right, sorry. So we ended up, hit a wrong button on my recording. So we were talking about H2S. We get that bent structure with the 2 lone pairs. So it is bent and polar. We'd have the dipoles going towards our sulfur, reinforcing each other, making this polar. So that's for the H2S. So we got a nice clear screen now to do our last one, the CH3F. So we've got carbon with 4 electrons, 3 electrons from those hydrogens, and then a fluorine with 7. So that gives us 14 electrons. We could put our carbon in the middle there and attach our 3 hydrogens, and then our fluorine. There we go. That uses 8 of our electrons, so we have 6 left, and we need some lone pairs on that fluorine to give it its octet, so that would use up those 6 electrons. So this is our structure. We've got 4 bonding domains and 0 non-bonding domains. That makes us a tetrahedral shape. Now a tetrahedral, again, if they all match, if it was all hydrogen all the way around or all fluorine all the way around the carbon, then we would be nonpolar. But with just that one fluorine, that's going to give us one dipole. The carbon-hydrogen bonds are nonpolar. So there's nothing to cancel out that dipole. There's nothing to on the other side that really cancels it. And even if we had 2 fluorines here, the tetrahedral shape, nothing is directly across from each other. So it's always going to be polar if they do not match. Okay, so this is our polar one. So that takes care of our 5 examples there. Hopefully you're starting to see how these work. All right, and last part that we're going to do is just talk about larger molecules. So analysis on larger molecules can still be done when there's more than one central atom. So everything we've done on this topic, so drawing the dot structures, analyzing their shape, their polarity, their hybridization, sigma pi bonds, all of that stuff can still be done. We just have to think about it around each central atom. So if we're looking for the 3D shape, we can determine it around specific central atoms. We won't talk about the shape of the entire molecule, but sections of the molecule. The hybridization is the same. It can be determined around each central atom because those central atoms are what are bonding and what creates those hybrid orbitals. For sigma and pi bonds, we can determine the total number of sigma and pi bonds for an entire molecule. Or it might ask between specific elements, like, hey, between the carbon bond or the carbon atoms, what kind of bonds are there? And then the last part, polarity. It's determined for the whole molecule. Unless it's a quite large molecule, then we may have nonpolar sections, and that's typically where we see carbon chains with just carbons and hydrogens. And then it might have a polar part where it might have an oxygen or a nitrogen or a chlorine or a fluorine, something like that. So we'll take a look at some examples of how we would analyze larger molecules here. All right, we're going to use these as some examples. So we've got this molecule drawn here on the left here. It's got these carbons all bonded, and then it has this OH part. Now I will go ahead and say this. When we have these carbon chains, where we have a bunch of carbons and hydrogens, those are called organic molecules. Organic chemistry is the whole study of carbon chain molecules. So both of these molecules you see on the screen would be considered organic molecules. They've got carbons and hydrogens. They might have little groups attached to them, like we see this OH at the end of this first molecule. They might have triple or double bonding involved, but they're organic molecules. So organic chemistry is an entire year of chemistry I took after the class you guys were taking. But we can analyze some basic things about these, even without doing full organic chemistry. Something I will say, this OH piece on the end of this also makes it an alcohol. So you guys might recognize OH as hydroxide. Well, when it's hydroxide is what we call it when it's in an ionic compound. When it's in a covalent compound like this, we call it an alcohol group. So that group makes it an alcohol. It would be called, let's see, there's 4 carbons. This would be called butanol. So there's different types of alcohols out there, and it's just how many carbons we have in our chain, and then where do we put the OH on the molecule. Okay, so let's take a look at our questions. This first one says, what is the shape around any carbon? And they say any carbon because that gives an indication that it's all the same, no matter which carbon you pick. So if we pick one of these carbons, I'm just going to circle that first one. It has 4 bonding domains, so that's going to make it tetrahedral. So around each of these different carbons is a tetrahedral shape. The second question, what is the shape around the oxygen? Now that's going to be a little bit different, right? So around that oxygen, we've got 2 bonding and 2 non-bonding. So in that case, this would be a bent shape. So if I could draw this a little bit true to what it looked like, that last carbon with its hydrogens, let's sorry, my H's are not that good, would then have the oxygen coming off, and then it would be bent with that second hydrogen, and it would have those lone pairs on one side. Okay, so if we drew it a little bit true to what it looks like in 3D, that hydrogen wouldn't be sticking off straight, and those lone pairs wouldn't be on the top and the bottom. The lone pairs would be on the same side of our molecule, and the hydrogen would be closer to the other hydrogens. So that is a bent shape for there. Number 3, what is a hybridization around any of the carbons? So if they have 4 bonding domains, that gives us sp3 hybridization. What is the hybridization around our oxygen? Oxygen has 2 bonding and 2 non-bonding, so 4 total domains. It would also be sp3 hybridized. All right, our total sigma bonds. So remember, sigma bonds are all the single bonds and one of a double or triple bond. So if I count my bonds, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bonds there. So we would have 14 sigma bonds. And then pi bonds, we don't have any double or triple bonds, so there's going to be no pi bonds on this, 0 pi bonds. I'm going to take the sigma off. And then our last part is to describe the polarity. Okay, well this comes into analyzing these larger structures and what's going on. This carbon-hydrogen end, this whole section of our molecule, we could say is nonpolar. Right? It's just those carbons and hydrogens. We've talked about them being nonpolar, those bonds. We don't have to worry about it. Our carbon-carbon bonds would be nonpolar. Our carbon-hydrogen bonds would be nonpolar. They're all tetrahedral. Everything's the same around our molecule. So that section would be nonpolar. But when we get to this section here at the end, where our O and our H are, we've got this bent oxygen. We would have a dipole towards that oxygen. I'm going to use this drawing I have up here. Those 2 dipoles point towards the oxygen, so they're going to reinforce each other. So it would be nonpolar for most of the molecule, mostly nonpolar, but polar at the oxygen. So when we get into our next unit and we start talking about how maybe this chemical interacts with another chemical, we'll be able to understand why this is important. It's important to see these pieces when they're on those larger molecules. All right, on this second one on the right-hand side, we've got just carbons and hydrogens. So it says for our first one, what's the shape around our first carbon? So that first carbon, we've got 4 bonds around it. 4 bonding domains, that's going to be tetrahedral. Then it says around the second carbon, if we look at our second carbon, it only has 2 bonding domains and no non-bonding. So 2 bonding domains makes it linear. So we have a nice linear shape there. Our first carbon, its hybridization with 4 bonding domains would be sp3. Where our second carbon with only 2 bonding domains would be just sp hybridized. Total sigma and pi bonds, so that's for the entire molecule. So our sigma bonds, I'm going to count 1, 2, 3, 4, 1 of these, so 5, 6, 7, 8, 9 sigma bonds. And then our pi bonds would be the other 2 in that triple bond, so we'd have 2 pi bonds there. And then describe the polarity. Well, here we only have carbons and hydrogens. That whole thing is made of just carbon-carbon bonds, which are nonpolar, carbon-hydrogen bonds, which are nonpolar. Everything's equal, so this would also be nonpolar for the whole molecule. Oops, LAR. All right, nonpolar for that molecule. All right, this is our last one. Why don't you guys pause and try this one. Try analyzing this larger molecule, and then when you're ready to check it, press play. Okay, so hopefully you've had a chance to work through this one and think about it. Let's check it. See if you're on the right track, if your thinking is correct. So our carbon, it's got 4 domains around it, 4 bonding domains, so it's going to be tetrahedral. We see that a lot with carbons. Our oxygen, it's got 2 bonding and 2 non-bonding. We see that a lot with oxygen, so it's going to be bent in structure. Our first carbon's hybridization. So again, 4 bonding domains. 4 domains makes us sp3 hybridized. Our oxygen has 2 bonding, 2 non-bonding, so that's 4 domains, also sp3 hybridized. All right, our next one, how many total sigma bonds? So let's count up those single bonds. 1, 2, 3, 4, 5, 6, 7, 8 sigma bonds. There's no doubles or triples, so we don't have any pi bonds. And then our polarities. So this is where we want to think about dipoles, we want to think about our shape, all of that. Well, first thing I'm going to do is kind of draw this a little bit more true to what it looks like. We've got our oxygen in the middle, and it's a bent shape. So instead of having that nice linear shape like we imagine with our dot structure, it would actually be something like this with our carbons coming off, and then we've got our hydrogens coming off of those, and we get this. So if we think about the polarity, oxygen and carbon, that would form some dipoles towards our oxygen, right? If we just looked at it in the linear structure, you might say, hey, these 2 dipoles point directly towards each other and they cancel each other out. But it's not linear, right? It's bent. Those 2 dipoles point towards oxygen. They are pointing in the same direction. It creates a polar molecule with that oxygen in the middle. So when you see oxygens, that is a big red flag that we're going to have some polarity going on where that oxygen sits, because that oxygen is not going to create a linear shape. All right? So hopefully you got that. You're going to have some extra practice, of course, with this in your pocket, so make sure you work through those. Ask me lots of questions when you get stuck, and we will work through this. Thanks, guys.